All right, so there's the recording turned on. So of course, the big event coming up later this afternoon after class is test number 3. That will be posted at 1:15, right? Okay. And so that will cover, well, things like we're on the test number 3 sample. I did have the answers to that, the solutions to that posted, and the video, but those are the solutions and the video are, those links are turned off until the test is over. You can still see the sample test, however, just without the solutions. So so that will start at 1:15, and then that will be posted at 1:15 right after class, and then that will be due at 5 o'clock on Thursday. So it's the usual system, right? So you'll write your answers and then scan those and then email those back to me by 5 p.m. on Thursday. And then I will post the solutions to that and post them immediately after the test is due at 5 p.m. on Thursday. So you will have those to look at, the solutions to test number 3, and then everything else prior to our final exam, because our final exam is next Tuesday, right? And that will start, it's Tuesday, May the 11th. If you look at this announcement on WebAssign, it's Tuesday, May the 11th at 12 p.m. That's when it will be posted. That's actually our scheduled final exam time, and then it won't be due until Thursday won't be due until Thursday at 5 p.m. So it'll be sort of the same time frame for the final exam as for the as for the other tests, right? It'll be exactly the same setup. There is a so of course you need to finish test number 3 first, right? And so but once you finish that, there is a review sheet posted for the final exam. And well, yeah, it just got posted. So that's with the sample tests in Blackboard, where all the sample tests are. There's a review sheet, and there are actually 2 separate postings. There's the review sheet itself. So that's just of course, just a list of questions. And then at the end of that, there are short answers in that same file. But then right below that, there's a more complete answer sheet that has actually the written solutions, not just the answers, but the step-by-step solutions to those problems. And with each of those solutions, there's a video that goes with it. So you can look at a video of the solution written out. What's a little bit different about these videos, though, is most of them are in MediaSite. They're not at MediaSite, which is the UHD server for storing videos, and so they're not in YouTube except for one of them. But the rest of them are in MediaSite. So when you click on the video, you'll have to log in to MediaSite using your UHD credentials. I don't know if you're gonna have to do that with every single video, or if you do it once and you keep playing different videos, if in the same session. But I don't know. You'll have to log in though at some point for those videos, because those are password protected. The YouTube videos are not, but those MediaSite videos are. So I tried a few and they worked fine, but if they're not working, I can't fix it, because I don't, if the videos aren't working, you'll just have to look at the written solutions, because I don't have access to MediaSite, so I cannot correct that at all, unfortunately. But hopefully they should work fine. So that is preparing for the final exam, right? Which again is next Tuesday. So you want to finish your test first, right? Of course, test number 3 first, and then go on to that. I wanted to point out that on the test number 3 sample, if you've worked on that, at the end of that test number 3 sample, there are some problems that says these are not covered till the final exam. Those are problems like we're going to talk about today. And so, and they're not really on this final exam review, they don't really have good problems like these. But again, those might be on the final exam. So you want to look at these problems 12 to 14 don't forget about those from the test number 3 sample. Those will be problems like we're going to do today, and they could be on the final exam. So but now I'll have to update my solution sheet for that test number 3 sample because I don't have the solutions to these problems there yet. But by the time you finish the test, they will be there. So if you look at problems 12 to 14, not 15, 15 is the last problem. So you can ignore that problem, but 12 to 14, okay, from that test number 3 sample. So just a warning about that. That's in that announcement that I keep pointing to here. And now then also Madison has a final exam review session on Friday, May the 7th from 1 to 4. So I, again, highly encourage you to visit that. Madison, I think I got this right. Here's the ID. The Zoom, I copied this from what 10 News sent. So here's the Zoom ID for that session, and there's the password, okay? So from 1 to 4 on Friday. So I think that would be highly beneficial in preparing for the final exam. Madison, during that session, if you would, are you conducting that session, Madison? The one from
Yeah, I'm going to be conducting that session on Friday.
Okay, if you don't forget to look at these problems. These are definite integral problems. So not indefinite, but definite integral problems, like at that test number 3 sample, just so they can have more practice with that. Now,
yes, sir. I'll be sure to cover those on my exam review.
Okay. Now remember, you have 2 homeworks that are due, but they're not due till Thursday. At the same time, the test is due. But these homeworks, problems like these homeworks, are on test number 3. They're on the sample test. You'll notice, and they're in these homeworks too. So if you haven't worked on these homeworks, try working on these before you actually do the test, right? Okay, and turn in the test. So be aware that those homeworks are due. And then you have this one last homework, which is what we're going to talk about today, but it's not due until the time of the final. And so these are problems like problems we're going to talk about today. There's a couple of those on the final. These are these problems 12 to 14 that I mentioned before. These are problems in this homework like those problems. So so we're going to talk about those today, but that homework is not due until the time of the final, right? So it's a little bit awkward that you're working on the homework, at the same time you're taking the test, which includes these problems. But I was trying to do that, of course, to give you as much time as possible to finish these homeworks, right? Okay. This one is optional, so I wouldn't worry about this one unless you just have a lot of time. Okay. All right. So if you have a lot of time and you want extra credit on the final, then feel free to work on this one. Otherwise, of course, these are the things, these 3, this one, and this one are the ones that are really important, right? Okay. All right. So I think I've sort of covered the key things there, right? Starting with today at 1:15, right, is when test number 3 begins. So we have no class on Thursday. So if you need to talk with me between, after class today, then email me so we can set up a time to have a Zoom session. All right. So, but today is our last class session. I will log on to Zoom next Tuesday when the final exam starts at noon, right? But that's not to do anything other than to answer questions for you. So if you urgently need to, ask me questions, then I'll be available next Tuesday at noon. Okay. So, but we don't have class. Today is it for class, right? Y'all are finally free from me after 1:15 today. Okay. Except for just finishing the test and so forth. Okay. So, all right. So so I've talked to. So, do y'all have questions?
Our text, the next test, test number 3 is this Thursday.
Yeah, it's due on Thursday, Mohammed, but it's posted immediately after class, right? It's the usual style. So at 1:15, the link will show up in Blackboard, and then it's due Thursday at 5.
Oh, so test number 3 we don't have till the Saturday, or?
No, test number 3 is due on Thursday.
Oh, okay. Yeah. Gotcha. Okay. Right. Glad that I asked that, or else I would have waited.
Yeah, I'm glad too. If there are other people that are I will probably send an email for people. We have some people who are chronically not showing up for class, but still turning in tests. So I'll probably send an email today from Blackboard with all the information I'm telling you now. So if it feels like I'm just repeating things, this is really for people who are, not logging in. Okay. So if you're logged in, you should know what you need to know, right? Okay. Other questions like that one? All right, so please don't be late with the test now, so that I can post the solutions to test number 3 at the time the test is due, 5 p.m. on Thursday, right? So you will have those available to you, right, to help you prepare for the final. Okay, so you'll know, if there are questions on this test that you were having difficulty with, you can see the solutions, right? So you won't repeat those mistakes on the, if a problem like that appears on the final exam. Okay. So the final exam is comprehensive, but as I mentioned before, it's it's the nature of calculus, right, to be cumulative. So if you're here at the end of the semester and you're keeping up, then you will be, trust me, you'll be prepared for the final exam if you spend time going over these review sheets and reviewing your tests, right? So of course you do need to spend a little time studying for it, but it's not like as I mentioned before, you're going to have to go back and remember things from the first of the semester that you've completely forgotten. Things from the first semester we're still using currently, so those will still be familiar to you, I think, for the most part. Other quick things there. Okay, so again, remember these homeworks on the are on test number 3, right? Okay, so spend some time with these before you work on that test, I think, right? Okay. All right, so I hope you've started on them currently, but if not, then today, right, and tomorrow before you do the test, then spend some time working on these, so you'll understand how to do in finding antiderivatives, right? We're going to practice that a little bit more today because we're going to look at some applications of antiderivatives right now, as a matter of fact, unless you guys have other quick questions that you want to ask me. Anything? All right, so let me switch back to notes here, and let me rearrange things. Let me tell you what we're going to do today. So this is the most important application of antiderivatives, but or I don't know, most important. It's one of the top 2 most important applications of antiderivatives, but when you see it at first, it looks like it's kind of a curiosity, but not something that's really super important. It's maybe an interesting application, but maybe not, doesn't seem like that practical or a super important application, but it actually is in practice. It turns out to be crucial. All right, so here's the problem, and this is kind of the problem, I think, that was one of the early motivations for calculus, this very problem. So suppose that you have a curve. But let's think of it as a continuous function. You can still make this definition without a continuous function, but let's assume that we have a continuous function here. All right, so here I've just drawn some continuous function. I don't have the formula written down for it. Okay, so who knows what the formula is, right? And so what we're going to do is think about this region between this curve and the x-axis. Now, since this curve happens to be above the x-axis, right, notice that this region then is the region below the curve down to the x-axis. Of course, the curve could be below the x-axis, in which case we might define the region between the curve up to the x-axis, all right? But as a first example, it's much easier to think about this as the curve above the x-axis, and we're interested in this region, this geometric region beneath the curve down to the x-axis. Now, if this curve, of course, if its domain is all real numbers, this curve may extend indefinitely to the right and to the left. So we want to limit the region a little bit because we don't want to end up with an infinitely large region. So we're going to limit the region here between two values on the x-axis. So we're going to assume that we're starting the region at some value a along the x-axis, and then we're thinking about the region up to a second value b along the x-axis. That's just to limit the size of the region, so the region is not infinitely large. Okay. All right. So here's a picture of this region that we're thinking about, right? So it's just a geometric region here, right? Okay. And now, what we're interested in doing is finding the area of that region, all right? So the area of this region, like you would calculate the area of a circle or the area of a square, right? Or the area of a triangle. We want to calculate the area of this region. So that's going to be measured in some sort of square units, right? Depending on how the x-axis is marked off. So it could be square inches or square meters or square feet, some sort of a square unit, right? Because areas are measured in square units. So see, we have kind of just a geometry problem here, right? We want to calculate the area of a region in the, on a flat two-dimensional surface, all right? In this case, the region just happens to be this particular region below this curve down to the x-axis between these two values on the x-axis, x equals a and x equals b. So that's our goal, all right, is to try to calculate that area. Now, you can see what's difficult about calculating that area, right, of course, is this curve is wiggly, you see, right? So this area doesn't have as its top edge here, it's not a regular edge, right? It's not like a straight line, okay? You have this curvy edge at the top. And so that makes this problem difficult, right? It makes the area difficult to calculate because we won't have a nice geometric formula that we can use to calculate this area, right? If this green area were a square or a rectangle, we know from geometry how to calculate areas of rectangles and squares, right? Or if it were a circle, we know from geometry, or a triangle, we know from geometry how to calculate areas of circles and triangles, right? Okay, but this area is a little bit unusual, again, because this top edge is this curve, right? Now, the bottom edge is just the x-axis, so that's easy. The left edge is just this vertical line. The right edge is just this vertical line, so that's easy. But it's this top edge, right, that's complicating things, right, because it's wavy. And so, again, we don't have a nice formula here from geometry to be able to calculate this area, right? Now, however, we do have a notation now that we're going to use to represent this area, okay? So this is the notation that we're going to use to represent this area. This notation represents an area. Notice, interestingly enough, it involves an integral sign, okay? So we have an integral sign. So you can already see, right, that somehow computing this area has something to do with integration, strangely enough, all right, something to do with finding antiderivatives. Now, however, what's unusual in this notation is notice that as a subscript and a superscript for your integral sign, you have two numbers. It's this, the left edge, A, right, of this area, and the right edge, B, of this area, right? Notice we're using those as subscripts, as a subscript and a superscript to this integral sign, right? Okay, this is now still referred to as an integral, but this is called a definite integral because it has these two numbers attached to it. These two numbers are called the limits, by the way, of integration. So this is the upper limit of integration. That's the where this region stops on the left, correct? And this number is, not surprisingly, called the lower limit of integration. That's where the region starts on the left, right, of this area. So and then here's of course, this is just the curve, right? And then, like all integrals, we end this with a dx. So this notation altogether, that represents a number, not a formula, but a number. And that number is supposed to be the area of this region. Now, I don't know what this number is yet. Okay, right? I haven't calculated yet. But altogether, that's what this notation means. Okay, it means this area beneath this curve down to the x-axis. And again, you refer to this as a definite integral because you have limits of integration attached. If you take the limits of integration off, which we've been looking at before, that's called an indefinite integral. All right, so let's take a look at a very simple example. We're not actually going to try to calculate any areas yet because we don't know how to do that yet, okay? But suppose we were given this graph, so x cubed minus 6x squared plus 4x plus 12, all right? That graph looks like this. Okay, so it's this nice blue curve that you see here. And suppose we wrote down this definite integral, all right? So we put this formula for the function f, right, as the integrand for our integration. And then we put these limits of integration to make this a definite integral, minus 0.5 and 1.5. So what would that notation mean? Well, that would mean the area beneath this curve, right, happens to be this blue curve in this picture, down to the x-axis. You're always finding the area between the curve and the x-axis, starting at where? Starting at minus 0.5 and then going on the x-axis, going up to 1.5 on the x-axis. So here's a picture of that area. That's what this definite integral represents. Between this curve and the x-axis, starting at minus 0.5 and going over to 0.5. So this green area that I've shaded in is the area that this definite integral represents. Again, now, we haven't talked about how to actually calculate this area, right? Okay. And again, the tricky part of calculating this area is the top edge of this area is this curve, right? So you get this kind of irregular shaped region. And, you know, we don't have any formulas from geometry to calculate the area of a region like this one, okay? If the top edge here were straight, right? If the top edge here were straight across, then maybe that would be easier to calculate, right? Because that looks like a rectangle. But here, because the top edge is this blue curve, this is going to be tricky to figure out what this area actually is. Let's see if we actually can calculate one, though. Okay, maybe we do have enough geometry to do this in some cases. So let's see if we can calculate this definite integral. All right, so let's see if we can calculate this definite integral. So what does this notation mean, right, to us? What is this indicating? This means the area beneath this curve, down to the x-axis, starting at 0 on the x-axis and going up to 3 on the x-axis. So we're talking here about the area of a geometric region. So when you see a definite integral, that is the integral with the limits of integration attached to it, okay, the lower limit and the upper limit, remember that represents kind of a picture to you. So it may be difficult to imagine what the picture looks like, because sometimes this curve may be complicated, okay? But still in your mind, you want to think, oh yeah, okay, here, this definite integral represents some sort of picture, the area of some sort of picture, all right? Let's see if we can, let's take a look at a drawing of that picture. It's not too actually hard of a drawing to make, because what sort of curve is 6 minus 2x? If you graph that, what do you get? What sort of function is that? 6 minus 2x, someone?
Linear.
That's linear. Yeah, thanks, Alvin. That's linear. So that's not too hard of a curve to even graph, right? So here I've made a graph of it. And so there's what this, here's what this definite integral looks like geometrically. Okay, it looks like this. This is the curve. This line sloping down is this line. So this is the a line 6 minus 2x. And we're going from, remember, we're going from x equals 0 to x equals 3. It so happens 3 is the x-intercept for this straight line anyway. So you end up getting this region, which is just a triangle. Right? And so we know from geometry how to calculate the area of triangles. You may have forgotten it, but it's easy to calculate the area of triangles. The area of a triangle is going to be the 1/2 times the base of the triangle. So that's the length of the bottom edge of the triangle times the height of the triangle. That's the height from the bottom edge up to the tip of the triangle. So the top vertex of the triangle. So in this case, this value is the base. That's the bottom edge of the triangle. And this value is the height, obviously, all right, for this triangle. So according to our formula from geometry, to calculate this definite integral, all you have to do is multiply 1/2 the base times the height. So that would be 1/2 of times 3. That's the base here, right? The length of this base is 3, because you're going from 0 to 3 on the x-axis. And the height there is 6, because you're going from 0 up to right here is 6 on the y-axis. So you get 1/2 of times 3 times 6, and that turns out to be 9. So this definite integral, we were able to actually evaluate it. We were able actually to figure out that it's equal to 9 because just because this curve is so simple, all right? And so we can rely on our geometry, but most of the time we cannot rely on geometry, all right? Finding these areas is more complicated. All right. I forgot what I was going to say. I can't remember. Okay. So let's go on to our, let's go on there. Oh, I remember what I was going to say. Again, notice when you're evaluating a definite integral, that is an integral where you have the limits of integration, remember you get a number, right? You get a number. If you take off the limits of integration, so if I had an integral without the limits of integration and you evaluate that, what do you get? You don't get a number. You get a what? You get a formula, right? Okay, you get a function. But when you have limits of integration, you get a number. So that's a big difference here between definite integrals where you have limits of integration and indefinite integrals where you don't have limits of integration. When you don't have limits of integration, that just means an antiderivative and you get a formula, you get a function. But when you have the limits of integration, you get a number out of that. That number is the area of a region. Let's try another one here. So let's look at this one. So this is the same curve, 6 minus 2x. So I have a picture of this, but now I want to know what is the area between that curve and the x-axis from not from just 0 to 3, but from 0 to 4. All right. So if you go from 0 to 4, here's 4 on the x-axis. If you go from 0 to 4 instead of 0 to 3, notice what happens, of course, right here at the x-intercept, the graph dips below the x-axis. So notice you get two different areas here, right? You get this area, which we already calculated. Remember, that area was 9, right? So we calculated that in the previous problem, but you also get this area, this little piece right here that's below the x-axis. But notice you still want the area between the curve and the x-axis. So when the curve dips below the x-axis, that area is going to be above the curve. When the curve is above the x-axis, that area is going to be below the curve. Now, all right, so that all seems simple enough, but here's here's one other important catch, okay? In calculus, we're going to think of this area as being negative. So in geometry, you would not think of this area as being negative, right? Because in geometry, we don't really conceive of negative areas. But in calculus, we're going to be a little bit more sophisticated. So we're going to measure these areas below the x-axis as negative numbers, So altogether, this area under this curve from 0 up to 4 will include a positive part and a negative part. And those two are going to cancel each other out a little bit. Let me show you how. All right, so if we want to evaluate this definite integral, right, that is the area between this curve, this straight line, and the x-axis from 0 to 4, well, part of that area is this part that we already calculated. That area is positive 9. And then part of that area is this part below the x-axis. That area is going to be negative because it's below the x-axis. When you add those two pieces together, notice they're going to cancel each other slightly. So you're actually going to end up with a value less than 9. Let's see what this area actually is. So this little area here, starting at 3 and going up to 4, notice that's still a triangle, right? This is still a triangle. So I can still use my formula from geometry to calculate the area of this triangle. Remember that formula is going to be 1/2 times the base. The base of this triangle is this part. What's the length of that base there? It goes from 3 to 4, so that's 1 times the height. The height would be this part for this triangle. Let's see, what's that height? Well, it's starting at the x-axis, and it looks like it's going down to -2 on the y-axis, right? So that height is 2. This height is 2. So, well, 1/2 times 1 times 2, that's easy. That's 1, correct? So this triangle has area 1, but it's negative because it's below the x-axis. In calculus, we're going to interpret that area as being negative. So altogether, this triangle has an area of -1. So you add the positive part, which is 9, to the negative part, which is -1, and altogether, you get an answer here of 8. So that's a little bit counterintuitive in calculus. Areas beneath the x-axis are interpreted as negative numbers. So you can get negative values for areas in calculus. Let's take a look at this example. Wow, this one's terrible. So I think this is the same curve we were looking at earlier, but I drew a little bit more of the curve. X cubed minus 6x squared plus 4x plus 5. Okay, so here is a graph of that curve. It's this blue graph, and so it's nice and wavy. Okay. So what was that? What's that function again? X cubed minus 6x squared plus 4x plus 5. So when you graph that, you get this nice wavy curve like this, okay? And we want to look at some of the areas between this curve and the x-axis. All right, so let's look at this area. From 0 to 1, here's my, remember, this is my big curve, x cubed minus 6x squared, et cetera, et cetera. All right, that's that function f. So I didn't write it all out. I just wrote f of x. And I'm interested in the area between that curve and the x-axis from 0 to 1. So starting at 0 and going over to 1. So that would be this piece right here, right? Okay, starting at 0 and going over to 1. Here's 1 on the x-axis. Now, I don't have any idea what that area actually is, but Van, here's my question. Is that area going to be positive or is it going to be negative? What do you think, Van? It's positive, right? Why do you know it's, so I don't know its value, you know, who knows what it is, but it's positive. Why do you know it's positive, Van?
Because it's above the x-axis.
It's above the x-axis, right? So that's just easy. So whatever that turns out to be, okay, 20 or 10 or whatever, it's going to be a positive number. All right, Van, now let's look at this one because this one's a little bit harder to figure out. So we want now same curve, but from 0 to 2. So we want to start at 0, and now we want to go over to 2. All right, so I want the area from 0 to 2. Now notice that includes this positive part, right? But it also includes this little piece right there because this curve dips just a little bit below the x-axis by the time you get to 2, Van. So notice you have a positive part here to this area and a negative part. Well, altogether though, what will this definite integral, what will this area turn out to be? Will it be positive or will it be negative?
It's also positive because the positive part is bigger than the negative part.
Right, exactly, correct. You said it perfectly. All right. The positive part is all of this, right? Okay. The negative part is just this little piece right here. Clearly, there's a larger positive area than a negative area, right? So this part is going to outweigh, the positive part is going to outweigh the negative part, correct? So altogether, you're going to end up with a positive area, right? Okay, so I have no idea what it's going to be, but that number is going to be positive. Let's look at this one. Let's extend our upper limit of integration just a little bit. So let's go from 0 all the way to 5. Okay, so notice now you have this positive area, but then you've got this big piece right here because you're going from 0 all the way to 5, right? So you've got this piece right here as well. So, so altogether, are we going to end up with a positive area or a negative area? Lance, what do you think there? Lance, are you there?
It's negative.
Yeah, okay. All right. Van beat you to it there, Lance. Okay. All right. Yeah, negative.
Oh, I'm sorry.
Right.
Are you still asking
okay,
me
Van.
or someone else?
All right. That's fine, Van. All right. So this is negative, Van, again, because the negative piece here, you can see it, right? You can just visualize it. This negative area is going to outweigh the positive area, right? This is a much bigger region than this one, correct? So when you add them together, you'll have more negative region than positive region. So altogether, this integral will turn out to be negative. What's the number? I don't know, okay? But it's going to be a negative number. All right, well, now we'll give Lance the really hard one here. Lance, are you there?
Yes.
All right, Lance. So I ask you the hard one. All right, since Van did so well there. Lance, what about if we go from 0 to 6? So now I want this area starting at 0 and going over to 6. So you have this positive piece, then you've got this piece, then you've got this piece. Altogether, what do you think? Is this going to be positive or is this going to be negative?
I think it's going to be negative.
You think it's going to be negative?
Yeah, just by looking at it.
You think this, so you think this region, which is the negative region, is larger than these two pieces combined?
I mean, like visually just looking at it, yes.
Yeah, it's hard to see though there, right? Okay. Yeah, this is a really hard one. I gave you the hard one there. I don't know the answer to this. Okay. All right. It's hard for me to tell, right? If I take the two positive, here are the two positive pieces, right? So is the area of the two positive pieces larger than the area of the negative piece, right? Who knows? Okay. So you know, this is kind of an ambiguous question, right? Okay, we really need some way of actually being able to compute this exactly right to determine if this is positive or negative. Our visual intuition is pretty good, but not perfect, right? So here it's really hard to tell. So different people might have different answers, and you know, we really need to be able to calculate this exactly. All right, to figure this one out. All right, so sorry, Lance, I gave you a trick question there, but I'm glad you made a choice there, though. Okay, because all right. Well, so now I need to show you actually how do we then how do we then calculate these areas exactly, right? Since our geometry is only going to give us get us so far, right, and our visual intuition is only going to get us so far. And this is where this is where calculus comes into play. And surprisingly enough, the answer turns out to be antiderivatives. Okay, so no one would have thought this. All right, that this problem of computing these areas of these irregular regions would have been related to finding antiderivatives. Okay, but this was an important problem at the beginning of calculus when people had important reasons for being able to compute these areas, but they were not able to do it, right? So this was a great discovery when they determined that, wow, this is really related to the problem of finding an antiderivative. And so this theorem is called the fundamental theorem of calculus. All right, so you can tell that's important because notice it's fundamental is the title, right? Okay, so in some sense, this is really one of the key theorems of calculus. There are only a few fundamental theorems, only a few theorems in mathematics labeled fundamental. There's a fundamental theorem of arithmetic, which says that any number any positive integer can be factored as prime numbers. That's called the fundamental theorem of arithmetic. And there's a fundamental theorem of algebra, which has to do with finding solutions to equations. Okay, well, this is the fundamental theorem of calculus. All right, now when you read this, it's very hard to read. Okay, here it is written formally out, but the explanation is much easier to understand. So oh, I thought I had a picture there of the explanation, but maybe it's in the prior notes. Let me see. Well, no, it's the same explanation. So let me explain it for you then with an example. Okay, so suppose that we want to compute this. Suppose we want to compute this definite integral. I haven't drawn a picture of this one, okay, although it's easy to draw a picture of this situation, but I didn't draw a picture of this one because I kind of want you to sort of not always be relying on having the pictures drawn, okay, although they are informative. And it's not a bad thing to draw the pictures, okay, but we're often computing indefinite integrals without having the pictures. But we can imagine in our mind the picture that goes with this particular definite integral. All right, and so what we have is this curve, 4x cubed minus 4x, right? Okay, so you graph that, you're going to get a curve. This is a continuous function. By the way, we're limiting ourselves to continuous functions here. So this is a nice continuous function. So when we graph it, we're going to get a nice, smooth, unbroken curve. And we want to find the area between this curve and the x-axis, but just a very little small area, starting at 0 on the x-axis and going up to 1 on the x-axis. All right. Well, you can imagine this curve is that's not linear at all, right? Because it's got x cubed in it. So this curve probably has some concavity to it, right? Okay, it's going to have some curvature to it, and in fact, it may have a bunch of wiggles in it, right? Okay, and so if we were to imagine this region, we can imagine that it's going to have a curved edge on it, right? Okay, and so it would be a difficult area to estimate. But fortunately, we don't have to estimate it because we have this so-called fundamental theorem, right? Here's what the fundamental theorem says, all right? What you want to do is find, so it's a very, very counterintuitive theorem. The fundamental theorem says, find the antiderivative, not the derivative. Find the antiderivative of this curve, okay? The antiderivative of this curve. So, you know, antiderivative seems just completely unrelated to this problem of calculating this area, but it's not, okay? All right, so we want to find the antiderivative of this curve, all right? So let's do that then. Now, of course, we have to do something once we found the antiderivative, right? This is just the first step in calculating the area. So first, let's find this antiderivative. Now, how do we indicate the antiderivative? Of course, you use an integral sign, right? Okay, but you don't put the limits of integration. So this is called an indefinite integral. Okay, so I want to find the antiderivative, the indefinite integral of 4x cubed minus 4x. So I denote that using the integral sign, right? But without the limits of integration. All right, so let's see if we can find this antiderivative. So this is something that's going to be on your test today, right? So how do we find this antiderivative? Well, notice these terms are just powers of x, right? These terms are just powers of x. So we can find the antiderivative just using the anti-power rule, right? So the antiderivative will be 4x to the fourth power over 4. That's the antiderivative of this first term. Remember, you're adding 1 to the 3 and dividing by that new exponent, right? Minus, and then let's see, for this term, we would have 4x squared over 2, right? Add 1 to this exponent is 1, correct? So add 1 to the exponent of 1 and divide by 2. Now, normally, of course, how would we finish this off? What would we add on here at the end when we're finding an antiderivative? What would we add here at the end?
Plus C.
Plus C, right? But it turns out that in this application of the antiderivative, you don't need the constant. The constant is meaningless to us. So we can just leave that off in this case. Because we're going to do something with the antiderivative once we find it, and that constant is not necessary to us with what we're going to do with the antiderivative. So in this application, you can just leave the constant off. So let's see, let's reduce this now. So here the 4's divide out, right? So you get x to the fourth power minus, and then 2 goes into a 4 twice, right? So you get 2x squared. So there is our antiderivative. All right, that's step 1. Now, what do we do with the antiderivative? Here's the great part. All you have to do is take your upper limit of integration and your lower limit of integration and plug those in to your antiderivative. So you evaluate your antiderivative at the upper limit of integration and the lower limit of integration, and then take the difference. So here's how I'm going to indicate this on paper. So I'm going to put in square brackets here. Here's my antiderivative. And I'm going to plug the 1 in and the 0 in, and I'm going to take the difference of those two results. The way I indicate that on paper, what I'm about to do is using this notation. This is very convenient notation. Okay, all right. So in brackets, there's my antiderivative, and I'm going to put the lower limits of integration, the upper and lower limit of integration here as a subscript and a superscript beside the bracket. What that means is what I'm just about to do here. I'm going to plug the 1 in for the x. So what happens when you plug 1 in for x? You get 1 to the fourth minus 2 times 1 squared. And I'm going to calculate that. And then I'm going to subtract off what I get when I plug 0 in for x into the antiderivative. So that's 0 to the fourth power minus 2 times, I'm running out of room here, minus 2 times 0 squared. So you see what I did? Plug the 1 in, the upper limit of integration into the antiderivative. Don't plug it into the integrand. Plug it into the antiderivative. Plug 0 into the antiderivative and take the difference in those two values. Let's see, what do we get here? This is 1 to the 4th power minus 2 times 1. That looks like -1, right? So I get -1 here. What do I get here? 0 to the 4th power minus 2 times 0 squared. Isn't that 0? So you get -0. And wow, that turns out to be -1. That's my answer. So that's the result. So what's that telling me about this area between this curve and the x-axis from 0 to 1? The fact that this turns out to be negative, what's that kind of telling me there?
It dips -1 like area below the x-axis.
Yeah, so this curve must, Dana, this curve must fall below the x-axis, right? Between 0 and 1, at least part of it, maybe all of it, right, has got to be below the x-axis, right? Okay, because otherwise this curve wouldn't turn out to be, negative, right? I mean, otherwise this area wouldn't turn out to be negative. Actually, if you graph this, I think what's going to happen is, I'm not sure, but if you actually do graph it, I think you have an x-intercept at 0, and also at 1, you have an x-intercept. And I think this curve drops down like this, okay? So, so the area does turn out to be below the x-axis. That's why we get a negative area. And actually turns out to be exactly 1, okay, or -1 square unit. Wow, see how easy that was though? Okay, so that's a complicated geometry problem because this, again, this curve has a, this function is a curve, right? Okay, so this area is an irregular shape, and but it's very easy with calculus to calculate that area, okay? Very easy to do. And the secret is just our knowledge of antiderivatives. So this was a really amazing discovery. This is right at the beginning of calculus. I think Newton's teacher knew this. Let's try another one then. Okay, so let's try this one. This would be so this is not an easy curve, to graph. I wish I'd drawn graphs of these, but I didn't. Okay, so my bad there. All right, so not an easy curve to graph, but this is obviously when you graph this curve, this is the cube root of x squared minus the cube root of x, right? When you graph this curve, you're going to get something that is definitely has some curvature to it, right? This is certainly not the graph of a straight line, right? Okay, so we're going to get probably a really unusual looking shape for a region, right? Because we want to go from 1 on the x-axis to 8 on the x-axis. All right, and I want to find the area of that region between that curve, whatever that curve ends up looking like, and the x-axis. All right, so so geometrically, that's a challenging problem, but from calculus standpoint, not really that difficult. Okay, once we know the fundamental theorem of calculus, which says, what do we want to find here first? So what's our first step? And that's really the only hard step here. Okay, so what's the first thing we want to do to calculate this definite integral? In other words, the area of the region that's described by this definite integral. What's step 1? Help me there.
Antiderivative.
Find the antiderivative, right? Find the antiderivative. Okay. So in other words, what you're going to do here is this problem you're going to do this, right? Take the limits of integration off and calculate this indefinite integral. In other words, find this antiderivative. So, so let's see if we know how to do that. So let's convert, as always in calculus, right? Let's convert these powers of x back, I'm sorry, these roots, right? Let's convert them back to powers of x. So how would you write the cube root of x squared as a power of x? That's x to what power?
2/3.
2/3. Yeah, perfect. I'm glad y'all said that, right? So the fact that you have a cube root means this is going to be a thirds, right? And then the 2 will stay as the numerator here. So the cube root of x squared is x to the 2/3 power. The cube root of x is just x to the 1/3 power. All right, so now we're finding the antiderivative of x to the 2/3 minus x to the 1/3. That's just powers of x, though. Yay, we just have powers of x. And so powers of x, easy to integrate, right? Just use the any power rule. So you would have x to the 2/3 plus 1, that's 5/3. So you have x to the 5/3 over 5/3 minus x to the 1/3 plus 1, which is 4/3 over 4/3. And now, normally, of course, when you're finding an antiderivative, you would put a constant here, but in this application, you don't need the constant. So you can just leave that off. Wow, let's see what let's see what all this is. If you divide by 5/3, that's the same as multiplying by 3/5. So you have 3/5 times x to the 5/3. I think that's the cube root of x to the 5th power. And then minus, let's see, this is 3/4, and then the cube root of x to the 4th power. Well, that's not the prettiest antiderivative in the world, but that's it, okay? So that's now what we will use in our fundamental theorem of calculus. So remember, what you do with the antiderivative is you're going to evaluate it at your 2 limits of integration, 1 and 8, and then take the difference of those 2 quantities, right? So I have 3/5 here, cube root of x to the 5th power minus 3/4 cube root of x to the 4th power. So I have to plug an 8 in here, and I also have to plug a 1 in here. Now, it looks like you need a calculator to do this, because 8 to the 5th power is kind of a big number, right? But don't panic, it's not as bad as it looks. So plug the 8 in first, right, into your antiderivative. Calculate that, and then subtract off what you get when you plug 1 in to the antiderivative. That looks a little bit easier, because you'll have 1 to the 5th power, which of course is 1, and then 1 to the 4th power, which again is 1. So that arithmetic doesn't look all that bad. All right, let's see if we can do this. See how much of this we can do without resorting to our calculator. I bet we can do most of it. All right, so I have 3/5 times, now this looks really hard because 8 to the 5th power is going to be a really big number, but actually it's not that bad, because what you can do here is take the cube root of 8 first and then raise it to the 5th power. So you do not have to take 8 to the 5th power first and then compute the cube root. You can compute the cube root of 8 and then raise to the 5th power. What is the cube root of 8?
2.
2. So what you really have here is 2 to the 5th power, which is 32. Okay, so not that bad. And same thing here. First, take the cube root of 8 and then raise it to the 4th power. Well, the cube root of 8 is 2 to the 4th power is 16. So you have 3/4 times 16. So not all that terrible. All right, and then here, these are easy, right? Because 1 to the 5th power is 1. The cube root of that, of course, is 1, right? So you have 3/5 times 1 minus, and then 3/4 times 1 again. Because 1 to the 4th power is 1, cube root of 1 is 1. Now, so maybe this is not all that terrible. Let's see, 3 times 32, I think that's 96. So we have 96/5 minus 3 times 16 is 48, but divided by 4 is 12. So I have 96/5 minus 12. Let's see, what do I have here? Well, 3/5 times 1 is 3/5. So you have this minus sign. So you have minus 3/5, and then minus a minus here would be plus. So that's plus 3/4. So we have 96/5 minus 12 minus 3/5 plus 3/4. That really is the answer. Okay, so once you've gotten here, you've really got the answer written down. The only question is, adding these numbers actually together, right? Okay, so let's go ahead and finish this. 96/5 minus 3/5, that's 93/5. And then we have minus 12 plus 3/4. Let's write that in terms of fourths. So this is minus 48/4 plus 3/4. So that is minus 48, minus 45/4, right? So all I really have to do here is take 93/5 and subtract off 45/4. Wow. Okay. So any suggestions for doing that?
Do you want to find a common denominator? Maybe 20?
You want to find a common denominator there, which is 20, right? Okay. You're exactly right. So so our common denominator here is 20. So multiply top and bottom here by 4. Okay. So multiply top and bottom there by 4. So if you multiply 93 times 4, what is that? 372? Am I doing that right? So we have 372 20ths. Multiply top and bottom by 4. And then here, multiply top and bottom by 5. So you would get, of course, 20 in the denominator. What's 5 times 45? Is that 225? So I have 372 minus 225 there, 20ths. What's 372 minus 225?
147.
147? There we go. So if we did our arithmetic right, there is our result, 147 over 20. A little bit more than 7, okay? So, so the area beneath this curve, right, from 1 to 8, there's the exact value. All right, so don't get hung up so much on the in the arithmetic calculations here, all right? Because once you have substituted your limits of integration, right, okay, you've essentially got the right answer. The rest of this is just doing some computations, and if you have to, you can rely on your calculator, okay? So the key thing is finding the antiderivative, correctly, and then substituting your limits of integration. After that, all of this is just arithmetic, okay? That's what the fundamental theorem says. So finding these complicated areas, a difficult problem in geometry turns out to be an easy problem for calculus to solve. Now, there are lots and lots of applications where we are calculating areas of such regions, okay? You might think that's kind of rare again, or it's kind of just a curiosity, but it's not, okay? There are many physical applications where we end up in solving a problem. It turns out calculating an area of a region such as the ones that we're working on here, okay? So that happens a lot in probability and statistics, but also in physical sciences constantly, okay? So that's why this application is important. Okay, now we have a couple more because we need to see some more examples. That's only 2. I've got lots of examples in the notes, but we're not going to go through all of them in here in class. But when you look at the notes, then you can look at the written solutions to some of these definite integrals that I went ahead and went through the steps in the notes, but we're not going to go through them here in class today, but they are in the notes. But we still have a couple more that we want to do. All right. So, but let's take a break here for a few minutes. So we'll come back at 12:45, and then let's look at a couple more examples of evaluating, calculating definite integrals. So remember, with a definite integral, you're going to come out with a numerical answer. With an indefinite integral, you come up with a formula because that is an antiderivative. Okay. All right, so let's pause there, and then we'll come back in about. Okay, I have returned. Yes, Saad, exam 3 is going to be posted today, right? So that's what I mentioned at the beginning of class. So if you're late, right, exam 3 will be posted at 1:15, and then due at 5 o'clock on Thursday, and then the final exam will be posted a week from today at noon. That's our normal final exam time, and then it will be due Thursday the 13th at 5 p.m. right? Okay, and there is a review now posted for the there's a review now posted for the final exam. So that announcement is in WebAssign, okay? And so read that announcement right here in WebAssign about the final exam review sheet. And then in a separate posting right below that, there's a complete solutions and videos that go with those solutions, that final exam review sheet. Don't forget these problems, 12 to 14, which are about definite integration, which we're talking about right now, that are on the test 3 sample. Remember, at the end of the test 3 sample, there's a piece of that that says these problems will be on the final exam. Those are problems very much like these examples that we're doing right now. And Madison will talk about those and other types of problems at 1 o'clock on Friday, okay? Because that is her final exam review session, okay? So, so are you guys back? Everyone heard that again for the second time? All right, so 1:15 today. That's when the test number 3. Okay, will start. Now it does not include test number 3 does not include definite integration. Okay, but it does have indefinite, antiderivative, indefinite integral problems right on it. Okay, and those are also the subject of the 2 homeworks that are due on Thursday. So as I mentioned earlier in the class, it would be good to look at those 2 homeworks prior to looking at the test. Okay, so try to look at those before you take the test, but keeping in mind that you've got to finish the test by Thursday at 5 so that I can grade it and return it to you in time, right? And so that I can post the answers to test number 3 in time to give you a chance to review that before the final exam. All right. Are there any questions about that? again, for anybody who came late? Any questions about those things? All right, are y'all still here? Anybody still there?
Yes.
Y'all are all eating lunch or something? Okay. All right, so let's do a couple more examples of definite integration. And but again, I've got as you can see here, solved examples, several more solved examples in the notes, right? Okay, so that we don't have time to go through all of these, but they're in the but they are in the notes, so you can look at these prior to the final exam. But definite integration is not on test number 3. Okay. Although it could easily be there because, right, the key part of finding a definite integral is finding an antiderivative, and that is on test number 3. This last example, whoops, it's in the notes. Just ignore that one, example 4, that I don't have solved. Just don't pay attention to that. Okay. All right, so let me see. Let's look at these last two here, D and E. Okay, I think we have time to finish these before 1:15. So again, these are just definite integral problems. So we want to evaluate this definite integral. Here we have a trig function, however, right? So that may make things a little bit, maybe make things a little bit trickier, right? So we want to find the area between this curve, pi times secant squared of x. Have no idea what that looks like, from 0 to pi over 4. Okay, so may turn out to be positive, may turn out to be negative, could turn out to be 0. Sometimes you get areas that turn out to be 0 because the positive and negative parts of the area exactly cancel each other, and you get an area of 0. Okay, all right. So step 1 here, right? Remember, we find the antiderivative. So we want to find the antiderivative of pi times secant squared x dx. And that looks like it could be complicated, but the thing to remember is secant squared, that is the derivative of a trig function, right? Okay, so you need to recognize that. What trig function has as its derivative secant squared? So can y'all recall that one? It's obviously not sine and cosine, but what trig function does have as its derivative secant squared?
Does it have something to do with tangent?
Yeah, it is tangent. Okay, so it does have something to do with tangent. Yeah, the derivative of tangent is secant squared. Okay. So I've been imploring y'all to remember the derivatives of the trig function, sine, cosine, tangent, right? Secant, cosecant, right? Cotangent, for exactly this reason, so that you can easily, well, write down their derivatives, but then also help you when you're finding antiderivatives. So, yes, the derivative of tangent is secant squared. So that means the antiderivative of secant squared will be tangent. So this antiderivative is easy to write down. It's just going to be, just keep the pi, because that's just a constant. So it's just pi times tangent of x. So this looks like it could be a terrible antiderivative, but it's really an easy antiderivative if you remember that that tangent's derivative is secant squared. All right, so there's our antiderivative. Remember, again, in this situation, you don't need to write the plus c, and so that means that to evaluate this definite integral, we are just going to use pi times the tangent of x. And we will evaluate that at 0 and at pi over 4, and then take the difference, right, when we do these two evaluations. So we get pi times the tangent of pi over 4, because I'm going to plug pi over 4 in first, right, minus, don't forget now you take the difference, and then pi times the tangent of 0. And so plug in that lower limit of integration, and hopefully those will be easy tangents to evaluate, right? But I think they are. What is the tangent of pi over 4? Do you know the tangent of pi over 4? Remember, tangent
One.
is it's 1. Yeah, great. Okay, because tangent is sine over cosine, and sine of pi over 4 and cosine of pi over 4 are both the same. The square root of 2 over 2. So since the sine and cosine are both the same at pi over 4, that means the tangent will be 1. So here you just get in this first set of brackets, you just get in this first set of brackets, you just get pi times 1 minus, and then we have to remember tangent of 0. What's the tangent of 0, though? So sine of 0 is 0, cosine of 0 is 1, and tangent is sine over cosine. So what will tangent of 0 be?
0.
0, exactly. So this is pi times 0. That's nice, right? So you just end up with a really nice area here. It's pi, okay? So the area between this curve, pi times secant squared x, and the x-axis does turn out to have a positive area. It's exactly the number pi. All right. Okay, let's try one more. So we want to find now what's this definite integral. So that's the definite integral from -1 to 1 of 1 minus x, that quantity squared. So in the usual fashion, right, we have to find first the antiderivative of 1 minus x squared. Now, I could find this antiderivative by, since this exponent is not very large, I could go ahead and multiply 1 minus x times 1 minus x. In other words, I could go ahead and square out 1 minus x times itself. And start that way. But just for further practice, let's try doing this. Let's try finding this antiderivative by substitution, because what we have here is a power, but it's not a very large power. But we do have a power of an expression, right? We have a power of an expression. And remember, when you have an expression raised to a power, that's often a good opportunity for integration by substitution. So let's just for further practice with integration by substitution, let's try doing this one by substitution. So I'm going to substitute u, my favorite substitution variable, for 1 minus x. So I'm going to call 1 minus x u. Now, when you make that substitution, right, you get, well, we're calling 1 minus x u. So we have u squared, and then we have dx, right? But we have to get rid of the dx, remember, because now we can't have the mixed variables here, right? So, and so remember, the trick for getting rid of the dx is come back to what your substitution is, which is u equal 1 minus x, and compute du dx, right? Take the derivative of u with respect to x. Be careful about this one now. What is the derivative of 1 minus x?
Is it -1?
It's -1. Yeah, it's not 1, it's -1. So be careful about that. It's actually -1. Now solve this for dx, right? So solve this equation for dx. So multiply both sides by dx. Of course, they cancel here. So you get du is equal to minus dx. But you don't want minus dx. You want just plain dx. You want to solve for plain dx. So divide both sides by -1. And you end up getting dx is equal to minus du. So that's what you'll plug in for dx up here is minus du. So I have u squared times minus du. That's what I want to integrate. So the minus sign you don't need, right? So factor that in front of the integral. Factor that in front of the integral so you can get it out of the way. So you have minus, and then the antiderivative of u squared du. Minus is just a -1, right? So you're really factoring a -1 in front of the antiderivative. Do not lose track of that minus sign, though. If you lose track of that minus sign, of course, you're going to have some sort of sign mistake in your final result, right? Well, now, how do you actually integrate u squared du? That's easy. That's just a power of u. So you can integrate that using the anti-power rule. So add 1 to the exponent, right, and divide by the new exponent. There, you've got it, okay? So this antiderivative is, don't forget the minus sign is there, u cubed over 3. But what was u again? That was 1 minus x. So you end up here with 1 minus x cubed over 3. And then the minus sign is there. So that is, don't forget, you don't need the constant here, right? So that is the antiderivative we're going to use to evaluate this definite integral. Okay, so all of this was supposed to be off to the side. Let's go back now and start and finish evaluating this definite integral. So what do? We take our antiderivative, which is minus 1 minus x cubed divided by 3. And remember, we're going to evaluate that at -1 and 1 and take the difference of those two numbers that we get. And whatever that value is, that is the value of my definite. Let's see. So you plug a 1 in here first, because that's the top, that's the upper limit of integration. So you get minus, and then, oh, that's not much fun, but you get 1 minus 1 cubed 3. So that looks like that's going to end up being 0 minus, and then let's see, minus, and then 1. Here we have to be careful. Minus a -1, because I'm going to plug the -1 in for x. So you have 1 minus a -1, all of that cubed over 3. And don't forget you have this minus sign there as well. So what happens here? I'm going to write all of this. So, well, 1 minus 1 here is 0. So 0 cubed is 0 over 3. So it doesn't matter about the minus sign. You're going to get 0. In this bracket, you get 0 minus. And then what happens in this set of brackets? Well, let's see. We have 1 minus a -1. That's 2. Positive 2 cubed is 8. So it looks like we have -8 over 3. Don't forget, we had this minus in front. So minus a -8/3 is positive 8/3. So there's our final definite. It's 8/3. So apparently, if we graph this curve, 1 minus x squared, if you graph that from -1 to 1, the area of that region between that curve and the x-axis is going to turn out to be exactly 8/3.
I'm sorry, I'm still confused on the first part, the beginning.
Which beginning?
Well,
Right here?
with a u and the dx stuff.
Yeah, right. So remember, Colin, last time we talked about integration by substitution, right? Okay, where we
Right,
substitute another variable for, well, essentially for x, right? Okay, so you remember you have I actually have them written in the notes here because I thought that y'all would forget this, right? Because they haven't practiced with enough. Remember, you have a couple of triggers for that. When integration by substitution might be helpful to you. It's when you have an expression to a power, not just x to a power. If you had x to a power, you could use the anti-power rule. But when you have an expression raised to a power, that's one situation where integration by substitution is often useful, okay? That's exactly the case that we had here. We had this, not just x squared, but we had this expression involving x squared. So when you see that, you should be thinking, oh, I might, sometimes this doesn't work, but in general, you might think, oh, I want to try using integration by substitution. The second case is when you have a trig function of an expression, not just trig function of x, but if you had trig function of, say, 1 minus x, or x squared plus 3 or something, you know, some expression involving x, a trig function of that, sine of that, or cosine of that, or tangent of that, then that's another situation where integration by substitution is often helpful, okay? So, but we were in this simpler case. We just had expression raised to a power. So what I did was, okay, I'm going to let u be that expression that's raised to the power. So I'm going to substitute u for 1 minus x. And see, the advantage of that is now you don't have an expression raised to a power. You just have u raised to a power. So see, this looks easier, right? Okay, you're simplifying the situation. But the problem is you've changed variables and you still have here dx. So you have to get rid of the dx. And that is this game that we play on here, right? You know, u is 1 minus x. So take the derivative of u with respect to x, which was minus 1, and solve for dx. So we get dx is minus du, and plug that in for dx. So you can get rid of the dx. That is integration by substitution. Now, once you've done that, you end up with this very simple integral. That was the whole point of doing the integration by substitution, is we get a very simple integral now. We know u squared du is easy to integrate. You just use the anti-power rule. But then you have to undo your substitution because you can't have u. Remember, the original problem had x in it. So you have to undo the substitution. We just have to remember, oh yeah, u was 1 minus x, right? So I just put 1 minus x in back for u. And that then is my antiderivative. And that's what I use now to evaluate the definite integral. So this part was just finding the antiderivative, right? Which turned out to be 1 minus x minus 1 minus x cubed over 3. Once I find that, then I use that antiderivative and evaluate the upper and lower limit of integration to get my.
Professor, why is it over 3 again?
What now?
Why is it over 3 again?
Why is what over 3? Why is this over 3?
Yeah, the negative u squared of
because
u cubed.
Because you're integrating, Saad, right? Okay, you're integrating. So you're integrating u squared. So you use the anti-power rule, right? You're going to do the reverse.
So add one. Gotcha.
Yeah, you add and divide, right? If you were taking the derivative, you would bring the 2 down and subtract.
Right.
But for antiderivative, you add and divide by this. That's the anti-power rule. Yeah. Okay. But again, u is not what I started with. I started with x. So now I have to plug back in where I have u. I have to plug in 1 minus x. So I get minus 1 minus x cubed over 3. And now I evaluate that at 1 and minus 1. I have one that's written out here already, but let's go through the steps. This is another integration by substitution. So let's go through the steps because I know integration by substitution is confusing. All right. So actually, there's a couple of them here. Maybe let's look at this one first. All right. So suppose we want to find this. This is now a definite integral, right? So I'm computing an area here, right, between this curve, whatever this looks like. It's probably an ugly looking curve, and the x-axis starting at 1 and going to 2. Okay. All right. So whatever that geometric shape is, I'm going to find the area of that. Let's see if I can move my. All right. Now, so first I have to find the antiderivative, right? And then once I find the antiderivative, then I plug in the limits of integration. So off to the side here, here's where I've computed the antiderivative. All right, so I'm finding the antiderivative of 3 over 3x plus 1 squared. Well, you know, in the usual calculus fashion, right, you don't want this power in the denominator. So we're going to move that to the numerator with a negative exponent. So that's just what we always do with calculus, right? So I'm going to write this as 3 times 3x plus 1 to the minus 2 power. But now, see, I'm back in the same situation as that prior problem. Here I have an expression raised to a power, right? If this were x to the minus 2, then this would be easy to integrate. But it's 3x plus 1 to the minus 2. It's an expression raised to a power. So this is a good opportunity for integration by substitution. So what I'm going to do is let u be 3x plus 1. See, I'm going to substitute u for this whole thing, 3x plus 1. Well, when you do that, here I've done it down here, you have, instead of 3x plus 1 to the minus 2, you have u to the minus 2, right? Okay. But now I also have to get rid of the dx. How do I get rid of the dx? Take the derivative of u with respect to x. What's the derivative of 3x plus 1? It's 3. That's easy. And now solve for dx. So when you solve for dx, you get du over 3. So where I wrote dx, I'm going to write du over 3. That's my final substitution. See, okay? I get rid of the 3x plus 1, that's u, and I get rid of the dx. I figured out that that was du over 3. Now, notice here a nice thing happens, because you had this 3 that was already there, right? And this 3 came about when we were solving for dx, right? So these threes will cancel each other. So that's just a lucky break on our part. These threes cancel each other, and I end up with just integrating u to the minus 2 du. But that's just a simple integral, right? I can just use the anti-power rule. That's just a power of u. So I just add 1 to the minus 2 and divide by the new exponent, which is minus 1. So I get u to the minus 1 over minus 1. That's the antiderivative. You don't need the constant in this case. Well, u to the minus 1 is the same as 1 over u. So I'm going to write u to the minus 1 is 1 over u. And then don't forget you're dividing by minus 1. So you get a negative sign here. So you get minus 1 over u. But what was u equal to? That was 3x plus 1. So finally, there is my antiderivative, minus 1 over 3x plus 1. And that now is what I will use to evaluate the definite integral. So you're going to plug 2 into minus 1 over 3x plus 1. You're going to plug 1 into 1 over the 3x plus 1. That's what I've done here. And you take the difference in those two quantities. Well, when you do the arithmetic, you end up with, if I did this right, 3/28. So see the integration by substitution here. Let me show you the last example that's written out in the notes. We won't go through all of it, but here's another integration by substitution example. Okay, so here we're finding a definite integral. We want what's the area between cosine of 2 times x. What's the area between that curve and the x-axis from 0 to pi over 2? So first, I have to find the antiderivative of cosine of 2x. Notice, if that were just cosine of x, that would be so easy to find the antiderivative, because you know what function has derivative cosine of x, right? That's sine. But this is cosine of 2x. So it's not just cosine of x, it's cosine of, it's cosine of an expression involving x. So see that, that's an opportunity for integration by substitution. When you have trig function of an expression, not just trig function of x, but trig function of an expression. So what I'm going to do is let u be 2x and substitute u in here. So you have cosine of u instead of cosine of 2x. And then here, when you solve for dx, you get du over 2. Well, altogether then, when you integrate cosine of u times du over 2, here's what you end up getting. 1/2 sine of u, and then plug 2x back in for u. So there is your antiderivative 1/2 sine of 2x. And now that's what you use back on the right-hand side, left-hand side, I mean, that's what you use to evaluate the definite integral. So plug pi over 2 into that, plug 0 into that, there's the arithmetic. Here you come out with an area of 0. So there's an example where area turns out to be 0. Okay, well, so you can look at these final definite integral examples from the notes there. Okay, all right. So we are out of time. So the test now should have shown up, right? So for y'all to take, right? But you've got a couple of days plus those extra homeworks, right? Those 2 homeworks on indefinite integrals, and then that final homework on definite integrals, which will be due at the time of the final, which is next Tuesday. All right, so I'll be communicating with you via email, right, between now and the final exam. So don't forget, turn your test in, and don't forget Madison's review session is Friday at 1. Okay, that's for the final exam. All right, I'm done. But if y'all need to ask me anything, feel free to ask me if y'all got any final questions here.
Hey, what time is the final?
The final will be posted at noon next Tuesday.
I'm sorry, what time is the next test due? Sorry.
When you say next test, you mean the one today?
Yeah, this test.
It's on. Oh, it's here. Here's Blackboard. Here are the final. By the way, there's the final exam review. This has the questions in it with short answers, and there is the solutions, the long solutions to these with the videos. Notice that's in the sample test part. But let's see if the test came up here. Yeah, there's the test, Lance. Okay, so there's test number 3, due at 5 p.m. on Thursday, right? Okay.
Got it.
Yeah, so it's there ready now.
Okay, thank you.
To work on. Okay. Other questions?
I have a quick one. Okay, so when we do our test, when we do the part where we replace the dx with the du, do you want us to like write it all down, or because I usually just do it in my head?
Yeah, no, write it down for me, Van. Yeah,
Okay,
write it down.
got it.
Okay. Yeah. So as usual, right? Be sure you're showing your work. Okay. Yeah. I know sometimes you can, especially on integration by substitution, you can see where it's going if it's not that complicated, and so you don't need to write things down, and that's fine. But for on the test, please write it down. Actually, Van, there's another reason to write it down as well, because in if you go on to take Calculus 2, you'll be doing a lot of integration by substitution, but those substitutions are much trickier. So you really have to write things down. So it's good to get into the habit of just writing things down.
Okay, got it. Thank you.
Okay. Other things then? Yeah, so as usual, be sure you show your work.
Is today or Thursday the last day of class?
Today is the last day of class, so we don't have class again. But I will. But if you need to communicate with me, email me. We can set up a Zoom session. But I will log on next Tuesday when the final exam starts. But that's just to answer questions. But we don't have class. Yeah, today is the last regular class day. I think it's the last regular class day, right? For all classes, I think today's the last regular class day. Final exams start tomorrow, I think. Is that right? Or well, I don't know when technically they start, but this is our last regular class day. Okay. All right, let me stop the